What we found is that there was always a big disconnect between what we would call the executive or the leadership team and the ground reality. And it's that messy middle where we intentionally surface the friction, surface what's going wrong, and then find a way to solve it. That gets me excited. You can even probably see the speed of my speech going up here. Forever, we've been trying to unite those three systems, but always hit the brick wall of the data structure problem, which is now pretty close to being solved. I co-founded with a gentleman named Dylan Dufresne, and our company name is Abelara. So our mission is to make digital transformation work for manufacturers everywhere. Everybody knows that ERP implementations suck.
There are more CEOs that have been fired because of an ERP implementation than hired.
Isn't it amazing?
I live in the just-in-time, just-in-sequence world. It's an amazing orchestra when it's going. How excited would you get if I said Fourier transform?
Oh my goodness. Even at 7 a.m. in Seattle, that is my favorite transform for sure.
Need to be efficient, make money, all that kind of stuff. That's kind of obvious. But I think from a systems level perspective, we need to put the product, the operator, the technician first and develop systems from the bottom up because we're all there to serve that. So I've been in the trenches for the past 20 years building production lines around the world. On this channel, I share with you my real-world experience for anyone looking to make a real impact in their factory. Whether you're a plant executive, an engineer on the floor, or anyone eager to expand their knowledge on this transformation topic. Let's dive in. So there was one post kind of in preparation for this that really stood out for me, and I never thought of it in the way that you described, where you spoke about how production line, or the philosophy of a production line, and you spoke about lean, and you spoke about MRP. And just watching that little video clip, I think it was like a minute or 2 minutes, not more than that, I started to understand and look at production lines completely different. So I'd love to open with you re-explaining that video on what is lean, what is MRP, and why they're diametrically opposed to each other.
Excellent, excellent. Yeah, that's one of my favorite topics, and it's often not clearly understood and can cause no end of problems, confusion, waste, etc. downstream. But yeah, we call it the manufacturing strategy spectrum. And the basic idea is that all manufacturing strategies exist on a spectrum, and we could consider one end of the spectrum to be the lean philosophy and the other end to be the MRP philosophy. What distinguishes them is in the lean philosophy, the most important facet is that it's customers that are pulling the goods through the factory, and the very act of the customer placing a purchase order and then the finished goods flowing out the back dock, metaphorically, that is what sends the demand signal upstream. And so the beauty of lean is if you can have a very smooth single piece flow with relatively uninterrupted motion of the goods all the way through as they're being operated, as they're being manufactured, you can do a really effective lean model. Lean tends to break down when you have a lot of variation in SKUs or a large number of different SKUs, and we'll get into that later. But on the lean side of the spectrum, the two key principles are number one, customer pull. It's the customer that's metaphorically pulling the goods through your factory. And the very act of pulling the good from one station to the next is what sends the demand signal upstream both within your factory workflow and to your suppliers so that they know that they need to replenish whatever goods. Now you can contrast that on the other end of the spectrum with MRP, manufacturing resource planning. That's entirely different in that here we are forecasting the future and we're pushing. So in this case, it's really us as the factory owners that are pushing a 6-month forecast upstream. And we say to each of our suppliers and to our supervisory personnel on the plant floor, this here is the 6-month plan. These are how many units of which individual SKUs I intend to make. So please be sure that all of the parts arrive on time, that you have the proper staffing and machinery, and any repairs that need to be done are done now. So the OEM equipment's available, etc. And what's really interesting to me is each has strengths and weaknesses. Neither is perfect, and I've never seen anyone that's operating purely at this end of the spectrum or purely as MRP. What you find instead is a whole host of pragmatic trade-offs on a spectrum that emphasize the benefits and or overcome the weaknesses of each of the philosophies.
So if I understand correctly, the downside of lean is obviously based on a specific customer order or set of orders. The line is adapting to that, and if there's maybe that may not be the most efficient way to produce that product, but it's being pulled by the customer.
Exactly.
Whereas with MRP, you have a, like you said, a 6 month forecast. So I can pick, like, if from transitioning from SKU 1 to SKU 2 is the most efficient transition, I should do that as opposed to transition from 2 to 7, because that transition might take longer, more tool change or whatever that might be. You can pre-plan ahead, you can build up the stock, but I would imagine you'd need the inventory would be higher on MRP, so WIP cost of WIP would be much higher, whereas with lean, it's ideally in theory supposed to be zero, right?
Correct. Yeah. And it never actually reaches zero, but as
No.
low as possible,
Yeah.
as you implied there. Yeah,
I think
exactly.
COVID told us that being too lean can be a problem.
For sure. And yeah,
When
the supply chain crisis post COVID was like nothing I've ever experienced in my career, but it really did lay bare the
Yeah,
lessons of where you are on that spectrum.
yeah,
And if you weren't aware of where you were on that spectrum, you had great clarity on it during that
yeah,
supply chain
for
crisis.
sure. Nothing like a crisis to let you know where you actually are.
For sure, for sure. And while I knew all of these principles before that crisis, my goodness, were they laid bare,
Yeah.
trying to run a factory during the crisis. But
And
yeah,
lean,
you have the right idea. And the key, there's a couple of things that make the inventory lower in lean. As you dig into the lean principles, the highest two level principles, as we said, are pull and demand going automatically upstream. Like those, the pull and flow, we could argue, are the two core principles of lean. As you dig in further, there's lots of principles about single piece flow, making sure that you don't have a lot of inventory and WIP building up along the process, and keeping inventory as low as relatively possible because you don't need inventory building up in different WIP stations, et cetera. If you can do all of that, then your factory has a certain capacity and you can respond to a certain band of quantities of product being requested from the customer. And one of the beautiful things is simply on account of minimizing the SKUs, because you have to have relatively few SKUs to implement a true lean program, you're naturally lowering the inventory overall.
yeah,
You run a factory yourself. We've all been tempted by, oh, there's this one special order. It's a new SKU, but it's really great product and a really potentially large customer in the future. And let's just do it. And so you do that, and it's great for this quarter, but then you do it again next month and again the following month. And 3 years in, you have 50 SKUs that are almost orphans that are customs that you build, but you need to support and you need to have inventory about.
yeah,
In the lean process, it won't let you do that. The system won't let you do that because there's no way to inject a new custom SKU into what is a really well-honed workflow already.
yeah,
And so you were perfect to point out that lean inevitably, when implemented properly, tends to lead to the outcome of super low inventories. And at the far extreme is just in time, where even the supplier only supplies the goods immediately when you need them from production.
yeah.
And I would say that that's the far end and not easily achievable. You wouldn't want to go from whatever state you're in today to a just-in-time model overnight. That takes some time.
Yeah. I live in the just in time, just in sequence world.
Do you?
Obviously,
Okay.
from an auto, obviously we're in the automotive space, and it's very much a German specific automotive, where based on where the vehicle is in about to drop from paint shop to body shop. I mean, sorry, from paint shop to final assembly, and as that drops,
Yeah.
then all of the whole supply chain is triggered. The cockpit, the axles, the seats, they start producing those individual components so that when that car eventually arrives at the seat fitment station, that unique seat arrives. It's an amazing orchestra when it's going,
Yeah, yeah.
but it's so lean that if the seat manufacturer stops, all the suppliers have to stop as well.
Exactly. And what can happen, hopefully it's not happening in your case, but what can happen, because even missing one of those parts, like completely messes up the entire orchestration, there'll oftentimes be finished goods inventory on the parts of at the sites of the suppliers. That's a
Mm.
buffer, if you will. They'll keep a
Yep.
buffer of finished goods inventory.
Yep.
So just in case, unfortunately, your machine goes down right when you're expected to deliver the cockpit or the dashboard or whatever it is, you've got something to sell. So ironically, sometimes just in time is code for the inventory is low at the OEM automotive manufacturer, say, but not at the suppliers. They're actually storing the finished goods
Yeah.
inventory, and that's what
Uh,
enables the
it
just in time.
gets um, it gets a little bit more interesting because you obviously have just in time, but then you also have just in sequence. So, as an
Yeah.
example, we're busy delivering an axle assembly line into Germany, and the axles are unique to that specific customer order. And the axle is produced by a tier one, so that there's no invent. You can't build up a stock of axles because
Ah,
that
okay,
axle is
okay.
unique. So even a cockpit, for example, because depending on the trim that you may have ordered, you might have picked the specific cluster with the specific steering wheel configuration and color of leather. There's millions of combinations. A lot of the key components like seats and axles and cockpits are uniquely built for that particular customer, and then they have to arrive not just in time but also in sequence,
In
which
sequence, interesting. Yeah.
which is
That's good. So just in sequence can prevent that. It sounds like you can't have finished goods built up on the part of suppliers.
no.
It's just the process doesn't allow it when you're doing just in sequence.
And you have 3 hours. So the on an axle, because I'm familiar with this process, the by the time the vehicle drops from paint shop into final assembly, that's when the tier one who's producing the axle gets the signal, and they have 3 hours to assemble the axle and deliver it because in 3 hours that vehicle arrives in the axle fitment station.
Exactly. Yeah.
Crazy. So super lean. Um, but when one little piece of the chain stops, like I said, if the axle is delayed, the seat guy can't deliver because his seat is sitting there waiting. The wrong car is there.
Exactly.
It's crazy.
Exactly. Which is hard, right? So
No,
it's
it's tough. It's
yeah.
tough, and the systems behind that are complex. Um, I did just want to kind of circle back to the lean versus MRP. Um, what is, from your experience, are there specific kinds of manufacturing? I'm thinking of, we spoke about cars, but there's oil and gas and there's FMCG. Are there specific kinds of manufacturing that are more uh, better or more efficient to work towards the lean side and the others that are more efficient on the MRP side?
Yeah, it's and believe it or not, it doesn't it's not the type of plant, but rather the nature of the product. And so more specifically, if your product line has a large number of different SKUs, and those SKUs are not like minor variations or firmware changes that you do at the very end at your final test station, it's super tough to implement lean. Lean requires a dedicated line with relatively single piece flow and no monuments all the way through.
Okay.
And you could only put so many cells like that and or linear lines in a factory in order to do that. And so it's not so much the specific industry vertical that you're working in, but really the breadth of your portfolio.
Okay.
If you have several hundred SKUs, all of them are quite different in nature. They're genuinely different products, not minor variants on the same thing. It gets pretty darn hard to implement a lean process, and you'll kind of be pushed towards the MRP end of the spectrum.
Okay.
If you have the good fortune of only having 3, 5, 10 SKUs, some relatively low number of SKUs that you build at relatively high quantities, then lean starts to look more and more attractive. And the spectrum is basically a balance between those two poles. So all else equal, the higher the variety, the more you're going to be pushed towards
Okay.
MRP, and the less the demand variation and the less the number of SKUs, the gravity will push you towards a lean model. And no need to go into them now, but just for awareness, some other philosophies like theory of constraints or DDMRP, which is one of my favorites, they can reasonably be put in a middle ground on that spectrum.
What,
TOC, as you know,
what is
I'm sorry, go ahead.
DDMRP? I don't know what
Oh, I'm sorry.
DDMRP is.
DDMRP stands for demand driven MRP.
Okay. Oh, okay.
It was developed maybe 20-ish years ago, and there's a textbook on DDMRP. It's a logical outgrowth from MRP. And as you'll notice, demand driven was sort of the principle on the lean side of the spectrum. MRP is all the way over here. So two really great operators. Last names were Peacock and Smith, Ptak and Smith. Carol Peacock and Chad Smith. They created this methodology called DDMRP, demand-driven MRP,
Okay.
which is fairly complex, but in essence, it tries to get the best of both worlds. It's a really healthy middle ground that gives you the benefits of both MRP and of the demand-driven side of lean. And it's a sophisticated process, but a really interesting one to study up on, even if a company ends up choosing not to go with it.
I'm gonna definitely read up on that. And obviously, theory of constraints is obviously looking for your bottleneck, right?
Yeah, exactly. Yeah, debottlenecking and find the bottleneck, loosen that one up, find the next one,
Yeah.
and rinse and repeat forever. And
Assuming there's unlimited demand.
exactly, exactly.
One of the other posts that you made was, I think you referred to it as the reliability dilemma, where you have maintenance systems not having access to real-time data.
Yeah,
Um,
yeah,
just talk us through I think you were talking about ignition connecting to maintain X in that particular post, but just
yeah, yeah,
principally, you obviously have a long history in the maintenance or reliability space.
yeah.
What was the essence of that comment?
Yeah, so the dilemma here, I'll set the context for just 1 minute if I could,
Yeah,
Yanesh.
yeah,
The difficulty here is it's very uncommon as of today to have your maintenance digital systems directly integrated with your operational systems. And there's actually very structural reasons that historically that hasn't happened. Specifically, if you think about what they call OT or operations technology, you'll see the standard Purdue model
yeah,
or ISA triangle if you Google that.
yeah,
And it's basically got 5 layers from ERP down to MES, SCADA, PLC, field instrumentation. And that's a really interesting model to study. What it doesn't make explicit, that is the problem for integration, is that at every one of those layers, you're dealing with fundamentally scalar data, or in the case of the ERP, with simple relational data, which is a slightly different thing. The problem is scalar data is great for operations and controls. Scalar data simply refers to pressure, a temperature, a flow rate, pH, anything where when you take a measurement, it's simply one number. And so the entire world of integration up and down that stack is actually pretty mature now. And it's, I'll say, relatively easy, assuming you have some networking infrastructure, to network all of these databases together using monitored OT tools. However, the implicit assumption in that entire ecosystem is that we're dealing with scalar time series data. And so they can as long as you're trying to funnel scalar time series data in any direction, you'll be fine with the existing integration tools in the OT stack. The problem is maintenance is almost always driven by non-scalar data. And so I happen to be a huge fan of vibration. That's my particular favorite technology. But there's 6 big predictive technologies like thermography and oil analysis and motion amplification. And all of them have super complex data structures. And the moment you try to take the data from vibration or thermography or motion amplification tensor and put that into your integration suite for your operational technologies, the thing breaks because it can only handle scalar time series data. And that's not what you're giving it. As a result, it's not so much that the world for years has wanted to integrate the maintenance world and the reliability, excuse me, the maintenance world and the operational world, but it's that fundamental data structure issue that stops it from happening. And so what's made me really excited is we're very close to solving that problem now. If you look at 3 different technologies, so let's look at a horizontal slice, if you will, with CMMS, with an MES or a SCADA, let's use SCADA system, and a predictive maintenance suite. Predictive maintenance, now in the vibration world, you can stream really complex data to an IoT-based predictive maintenance suite that it was built to handle all of the really complex data structures and perform lots of great AI and diagnostics over there. I love that world, and given the opportunity, I'll talk about that for an hour
yeah,
straight. But the basic idea is they're able to consume all of that data in the cloud typically, but it doesn't have to be. And then while they ingest vector, matrix, and tensor data, they can spit back out simple scalar data that the OT ecosystem is able to absorb. Specifically, things like the presence or absence of any kind of a machine flaw, a severity level on that machine flaw, or a simple overall vibration as contrasted with a really complex data structure. So now you have an IoT vibration suite. That data can very easily go into a SCADA system, such as Ignition from Inductive Automation is one that we work with
Yeah,
quite often because it's open, it's composable, it's everything we love about a
yeah,
SCADA system. And now you can also integrate that to a CMMS that doesn't even have to be on site; it can be in the cloud. And in this case, we were talking about MaintainX is one of my favorite CMMSs. Until just a few years ago, it really wasn't possible to have those three systems working together. But now they're natively integrated. So if you look at recent announcements, Waits has announced a partnership with MaintainX where their data can go directly to MaintainX. If you prefer, or if you already have Ignition, the Waits predictive maintenance data can go through Ignition and then be housed there with MaintainX data as well. And all of them can be aware of the alarm status of the other two. That's something that's new. That's what I got so excited about with that post is forever we've been trying to unite those three systems, but always hit the brick wall of the data structure problem,
yeah.
which is now pretty close to being solved.
So is the using weights as an example, um, transmitting the vibration data, which is high sample, very, very, very data or large volumes of data
For
in
sure. Yeah.
three axes, X, Y, Z,
Yeah.
um,
Yeah.
into through ignition into maintain X. Where's the decisions being made in that
Yeah.
architecture?
So it's a little bit the other way. So in the case of vibration and in the case of weights, because the OT systems don't know what to do with non-scalar data, you do all of the analysis of the complex data inside the IoT suite.
Okay.
And the vibration used to be dominated by a physical walk-around box. They called it a route collector.
Yeah.
Increasingly, almost all modern vibration systems are driven by IoT, are driven by a cellular connection to the cloud, and all of the complex data is streamed there. So what happens now is the complex data is collected by the vibration IoT system. It streams that data to the cloud, to their own custom software, which was built to handle this complex data. And then what they send back to the other systems is scalar data that those systems can absorb. So although they can't absorb things like time waveforms and frequency spectra and all the complex plots that I love to wallow in and figure
Yeah.
out what's happening with a machine, they can't absorb that stuff, but now they don't have to because you can basically operate on the complex data and send out a scalar summary that they can accept and are more than willing to. That's the difference here that really just wasn't there even 3 to 5 years ago. And that gets me excited. You can
Yeah.
even probably see the speed of my speech going up here.
I was just thinking to myself, how excited would you get if I said Fourier transform?
Oh my goodness. Even at 7 a.m. in Seattle, that is my favorite transform for sure.
Yeah, for sure. I failed that course in university, but I only appreciate it now.
And if you want to geek out after hours, I'd be happy to talk through it, Dinesh. It's really incredible. It
Yeah,
shouldn't
yeah.
work. It defies all logic and intuition.
It,
For the
it,
first 6 months of studying it, I still didn't believe it. Even when I watched the math work, I'm like, this is the least intuitive thing I've ever been a part of. I can't believe it works, but somehow it does. And
I remember studying it and thinking, why on earth am I even studying this? It makes no sense. Until I looked at a vibration profile and then somebody did a Fourier transform and then I like, now I get it. I should have studied harder for that course.
yeah, we're lucky in the mech. I think you were an electronics engineer or maybe mechatronics. Is that right,
Mechatronics,
Yanesh?
yeah.
Mechatronics.
Yeah,
Okay.
yeah.
We're lucky in the mechanical side because there's this very physical interpretation of what's happening with the Fourier
Yeah,
transform that's not there if you approach it from like a double E side. And
yeah,
I think we mechanical engineers are lucky in that respect.
yeah, for sure. Um, but maybe let's geek out a little bit about on the vibration sensor side.
Yeah, yeah.
Um, the what's I've got a couple of questions, so let me rattle them off as they come
Yeah,
around.
no,
The first one was, what's your take on sample rate of a
yeah,
vibration sensor? Because I think a lot of people just think that, okay, if I slap on a vibration sensor, it's gonna give me some sort of, I'll be able to do some predictions. But if you don't sample at the right rate or fast enough, you miss the
exactly.
information. But at the same time, if
Correct.
you sample too much, how do you transmit gigs and gigs of data per day on from one sensor and you have 50 sensors inside a factory? What's your take on that?
Exactly. Yeah. And what's great about your question, Yanesh, is implicit in the way you asked it. It showed that you understand the distinction between overall vibration and full spectrum vibration.
Yeah.
For the listeners, let me just describe that first, and then I'll explain the philosophy on sampling rates and things. But oftentimes people will put in a vibration sensor and then stream it directly to their OT systems, not realizing that what they're doing is sending a super simplified value of the vibration. So in the vibration world, it's very common to sample at 10 kilohertz or higher when you're taking a vibration reading. And 10 kilohertz simply means 10,000 samples per second.
Yeah.
So if you were to say to me, hey, Glenn, please go take a vibration sample. When I take one sample, what that really means is sampling 4,096 typically, 4,096 samples at this absurdly high rate of 10,000 samples per second. And what that allows you to do is then look at a full spectrum or time waveform of data. So kind of misconception number one that you clearly understood because it was implicit in your question is if you just put a vibration sensor in and you're doing nothing else and just sending the output directly to your OT system, it's virtually certain that what you're doing is sending what's called an overall vibration, most commonly an RMS value of the entire vibration spectrum. That has some value, but not a lot. Consider that like a blunt instrument compared to a really fine surgical scalpel. It will give you just a vague idea of whether the vibration is trending up or down, but it won't give you any specificity about what failure mode you might be having. In contrast, if you can read up to 10 kilohertz, which because of the Nyquist frequency, you have to then sample higher. You have to sample at 20 kilohertz or higher.
Yeah.
You can get the vast majority of the diagnostics that you need. So my philosophy is you're above the Pareto optimal point if you sample 20 kilohertz or north. 20 kilohertz or higher than that, which then lets you analyze 10 kilohertz or higher nominally. Then you're in a good spot for vibration diagnostics. But as you said, that means you have a whole lot of data that you have to then stream to the cloud or to a collector device, to a server on site, wherever you happen to be sending it. Go ahead, Ed.
Yeah,
I'll let you ask your question before I
and
continue.
you would separate X, Y, Z, right?
Exactly. And yeah, and very well stated. Each sensor tends to be actually three sensors in one. It's a triaxial sensor, they call it, with X, Y, and Z, X, Y, and Z. And so there's really 3 times 20 kilohertz sampling on each of the channels. That's a lot of data.
Yep.
And so what has happened is the trade-off really is, believe it or not, it's less about the cost of sending that data and more about the battery life.
Yep.
So for sure, it does cost money to send that much data to the cloud, but the more binding constraint is the battery life. And the industry has kind of come to a nominal average where customers are expecting 5 years. If they put a vibration sensor out there, they expect it to go for 5 years, and then they'll replace a battery so they can get another 5 years out of it. So that's the norm that the industry is expecting. And in order to do that, depending on the manufacturer, it can vary, but roughly you can do 1 full spectrum reading per day, something like 12 to 24 overall readings per day. And if you happen to be capturing scalar data like temperature, which many of those sensors do, you can do that every 15 minutes or so.
Yeah.
And so these are estimates, these are rough numbers, but if you think every 15 minutes for scalar data, every hour for overall vibration, and once per day for full spectrum vibration on all the channels, that will lead to roughly 5 years of sensor life. Okay. And that's kind of the happy medium that the industry has settled on.
Okay, that's interesting. So yeah, I've always been fascinated. How big are the sensors?
Yeah, they're relatively small. In fact, I have one in the drawer here. Let me get one out. And so this is from a company called Weights. They're a leader in the predictive maintenance space. And as you can see, it's just a few inches. The sensors are relatively small. Admittedly, Weights did a great job of designing a really low footprint sensor. So this is on the smaller end of what you'll see. Yeah. But this is about the size, just a few inches, less than an inch in breadth. And you can fit them in most places. And in cases where things are too tight to fit this, there do exist some specialty sensors. If I have one handy, I'll pull one out. Yeah, here's a good example also from Weights. You can connect a very small sensor like this into a really tight squeeze.
Okay.
What makes this sensor large is not the piezo sensor itself, or excuse me,
Yeah.
it's a MEMS sensor, not a
Yeah.
piezo. It's not
It's
the
tiny.
vibration
Yeah.
sensor itself, it's the circuitry. You need circuitry inside for wireless, and you need to hold a battery.
Yeah.
If you offload all of that into a different device, you can get only the MEMS sensor in a tiny little footprint like this, and you can see that this is, a centimeter max in
Yeah.
each dimension,
Yeah.
and then put the wireless circuitry in a different box that
Box.
you're connecting this to, and that lets you snake into any area,
Yeah.
hazardous areas, areas that you can't fit that sensor into, etc.
Yeah. MEMS sensors are tiny. Uh,
Yeah, they're really tiny. It's nice. It's far smaller than the piezo crystals that we used to have to use, and even more importantly, far less power consumptive. That's really what there was a handful of things that had to happen for the IoT world to really take off in vibration. And if I go back to the early aughts, if you will, like I graduated in '01, and even then they were saying IoT vibration, it's the thing of the future. And to be fair, they didn't say IoT. That wasn't a thing back
yeah.
then. But they did say they did say wireless sensors, wireless vibration. What a great time that you graduated, Glenn. That's going to take over the world. And it took 15, maybe 20 years from that point for it to get really mainstream adoption. And there were dozens of practical problems, the most important of which was cultural adoption of wireless systems on site. People until recently were very averse to having any wireless system whatsoever on the plant site for a variety of reasons, most importantly, concerns over reliability and security, but then also the power draw, like implicit in the assumption that back in 2001, wireless vibration was going to take off. We assumed that the energy harvesting capabilities of the technologies at the time were on this exponential curve and would very quickly make it batteries not necessary. You would simply harvest the energy from the vibration of the machine that you're monitoring in the first place, and then all is great. The thing will last forever because you're harvesting the energy that you need to send the signals.
Yeah.
Interestingly, that didn't pan out. I was as convinced as anybody that energy harvesting was the wave of the future.
Yeah.
But when cell phones came about, and eventually when electric cars drove more battery technologies, almost nobody uses energy harvesting today. The industry is dominated by low-cost lithium-ion batteries, and that's where we landed. But that's one of many reasons it took 15 years to actually get
Yeah.
that market to take off.
And if I understand correctly, I think the MEMS, obviously cell phones were the drivers of the MEMS sensor.
They sure were. They
Yeah.
sure were. Yeah. Do you guys our age, Yanesh? You can probably remember the first time you saw a cell phone where you held it in one direction and then flipped it, and it automatically changed the orientation of
It
the.
was
It's.
crazy.
I know. I mean, my kids. It's a default assumption that that's
Yeah.
the world has always been that way,
Of
right?
course.
And but but the literally that same technology that's using a MEMS accelerometer, and admittedly the ones that we use for industrial purposes are specialty designed, and it's not literally the identical same one. But we would never have had the technology curve advance without that flipping of the cell phone and using an internal MEMS accelerometer.
Yeah.
So in a very direct way, we, the vibration industry, are direct beneficiaries of that
Yeah.
cell phone technology.
And the
Our industry wouldn't
batteries.
exist as
Yeah.
it does today without it.
And the battery tech, right?
And the battery tech, yeah, which was driven both by the cell and by the automotive industry. And so, yeah, and
Speaking of kids, over December we stayed in a hotel, and I've got a 6-year-old daughter, and the hotel had a phone with a like you lift it up and there's a cable attached. So
yeah,
we were staying with some family, and they were staying in another room, and her cousin also had never seen the phone, similar age, and they just couldn't get over talking to each other on the phone, like in the room next door, because it had a cable, and they could press the buttons to dial the room number. And that
that's
was like
amazing. Yeah.
fascinating for them. That was like they'd never seen it
I,
before.
they'd never seen the object. Extra credit if it had that rotary dial that was
Yeah,
like
yeah,
zing,
yeah,
zing, 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 zing,
yeah.
zing.
That yeah, that the hotel was a little bit more advanced than that.
Yeah. Yeah.
Um,
Ironically, we got my kids one of those for Christmas this past year.
oh, okay.
There's a local family turned entrepreneurial made phones just like you and I grew up with, except
Okay.
you plug them right into an Ethernet port in your house. Otherwise, it exactly resembles what you and I grew up with on
Yeah.
phones, and so you can tightly control who they can call, only their friends' numbers, and it operates just like an old school phone like you and
That's
I
cool.
had, which is really nifty. I had
That's clever.
a strong feeling of I just lots of
Nostalgia.
childhood memories came. Yeah, exactly.
Yeah,
You have to sit on the bed and you have to be within 6 feet of the thing where it's plugged in. And
of course. So you spoke about the difference between reliability data and operational data.
Yes.
And um, the there was also an interesting post that I learned a lot from was the naming hierarchy um,
Yeah.
in a reliability space and in let's call it the operational space. And you touched a
Yeah.
little bit
Yeah.
about the UNS, which from what I understand is definitely more on the operation side. Um,
Correct. Yeah. It's
and CMMS or digital maintenance platforms are obviously on the reliability side. How do you resolve those two from a data structure, a naming hierarchy perspective?
Yeah, and I'm thrilled that you asked it because interestingly, resolving that problem properly is the most important success factor for any type of AI or advanced analytics initiative that your plant might take on. And so, yeah, UNS, most UNS proponents would say they're trying really hard to harmonize all of those worlds. It's absolutely true that, UNS thinking came out of the operational technology stack, but they're making a conscious effort to include operational technology, maintenance technology, and what you would call traditional IT information technology or the ERP system and the associated financial systems. What's really interesting there is if you think about it for just a second, walk out onto your factory floor. There's some big machine there that's doing production. That machine can be looked at in different ways. From the production side, if you have an MES, that machine is a resource that, in order to operate properly, it needs certain raw materials to flow into it. It needs to be available at the right time for this production batch run or this linear run. And it needs to be up and operating properly. And if it has those three things, and sometimes a skilled operator, depends on the machine, but for the moment, let's assume you need a skilled operator. All of that is surprisingly difficult to coordinate, and it's usually done either manually or in a system called the MES. Now, if we stare at that same machine through a different lens, through the maintenance lens, that machine is something that we need to monitor so that it doesn't go down unexpectedly. And we have to, number one, identify flaws in advance so that we can proactively schedule repairs. And number two, make sure that we're coordinating with the operations team so that we don't take the machine down for preventive or predictive maintenance tasks when they need to be running an operations run. The way that the MES does that uses the language of routings. So normally they would talk about work centers and routings. And the ISA standard, ISA 95, has a really sophisticated language that you can use to describe like that machine right there. How do I describe the people that need to be associated with it, the parts that need to flow through it, and where it resides in the overall process hierarchy? Similarly, the maintenance team has a way, they call it the asset hierarchy, a way of identifying where that machine is in the overall plant and where I need to, for their case, it's more important to understand where do I need to tag out the electricity so that nobody gets hurt? How do I make sure that I isolate all the valves that are leading into it? So they have a different reason that they need to know exactly where that is. But they use the asset hierarchy and the associated prints and engineering schematics to figure out how to do that. The point of going into so much detail on both of those is today it's very rare to see those two integrated. But it seems obvious, right? So many of our projects right now are doing exactly that, are integrating the asset, what's called the asset hierarchy in the CMMS, and I shouldn't say integrating, I should say harmonizing. Harmonizing the asset hierarchy in the CMMS with the routings and the method of specifying the machine from an operations perspective, a la ISA 95 is the most popular naming scheme. If you don't have those lined up, then you're speaking completely different language in the CMMS versus the MES. And so it's really important to figure out the appropriate level at which they must be identical, and then the level at which the two can diverge without hurting one another.
Yeah.
And normally that comes down to the big machine level. So if you have anything resembling a machine train, like a motor driving a piece of equipment, or like a single PLC on a skid driving that skid, that is the level at which you tend to want to harmonize them, meaning you call that object the same exact thing. And then above and below, you can have some mild differences. But if you match the naming right there, then it's easy for the maintenance team to say, that's the machine that I need to take offline on September 13th to do this bearing replacement because I know that I've got a bearing flaw
Yeah.
happening. That's one suggestive example, but it gives you the spirit of what the UNS intends to do. So the UNS is a unified namespace, and it basically says, okay, every single of we have 10 or so big industrial applications. Every one of them has something resembling a namespace. By namespace, we mean in the maintenance world, it's an asset hierarchy. It's a hierarchical cluster of assets that lets me know which asset I'm working on and how they're organized in the plant. In the operations stack, like we said, ISA 95, it is a routings. The language of routings is much more common. Routings and work centers is much more common as you talk about the namespace there. And then the ERP, of course, it's the master chart of accounts. The master chart of accounts tells you how to label any transaction, which work center or which cost center it should be transacted against. Likewise with suppliers that are outside of the company, et cetera. The UNS aims to solve the problem of, okay, where do these need to harmonize and be the same in order to exchange meaningful information? And where can they diverge in order to optimize inside of their own box? That is very much more art than science, but the founding principle of UNS is that you can't simply dump all of that into the metaphorical cloud. Like, oh, we've got 10 applications, super. Dump everything into the cloud and just point an MCP server at it, and all will be well. Everything will get figured out. It turns out that doesn't work for many reasons that we can dive into, not the least of which is harmonizing of the naming conventions and the different data structures from scalar to tensor. But long story short, you can't just dump all of that into the cloud. You need some type of a unified structure that's carefully thought through that today cannot be automated. So I've not seen anyone automate that difficult process of figuring out the optimal UNS, the optimal naming structure that connects all of those together. The beautiful thing is once you do that hard work, number one, you have a ton of insights. It makes you start to think hard about what the people adjacent to you are doing. If you're a maintenance person, you'll all of a sudden understand far more about operations that you ever did before by just going through this process. But number two, it's super easy to then do all of the more advanced stuff. Once you have a UNS well thought through and in place, it's much easier now to do more advanced analytics, apply a whole bunch of different AI tools, either in concert across multiple applications or like a deep dive down one application. But it's that constitutive glue, if you will, the UNS, that's the hard work you have to do on the front end to make all the other stuff work well.
And I think most factories don't think like that. They kind of dive in, then realize they need something from maintenance, but then they've already diverged too early on. I would add one layer of complication to that I've experienced is quality department. So
oh yeah, please.
Like a simple example of a leak tester, like a leak test thing, requires the production guys to know about the leak tester because the leak tester is used to produce the product. The maintenance guys, as you say, also need to be informed about the leak tester and predict when things need to happen or when they need to do a calibration or whatever that needs to be done. The quality department looks at the leak tester very differently because they want to know that the product that's being produced has been tested correctly. And when there's failures on the leak tester, quality department gets involved and they talk, I guess, closer to the operational guys, but differently because they talk about the process, not the asset. And the maintenance guys are talking about the asset, and production guys are looking at throughput, and then they move away.
Yeah, that's an outstanding example of Ganesh. And can you describe the data that comes out of that lead tester? It's because quality faces the exact same problem that maintenance faces, but it's an awesome example that you raised. Yeah, what comes out of that lead tester? What's the nature of the data?
Yeah, so obviously depending on the product, but I'll talk about an engine because we've made production lines that assemble engines. So in an engine, you've got an oil chamber and you have the water chamber. So when you apply a leak tester, typically you would apply two leak testers, one to the water chamber to make sure that the engine is assembled correctly and there's no leaks from the water. And you typically get we would do a pressure decay. So you'd apply a certain amount of pressure, a bar, and then you'd have a period of time where you would wait and then the pressure would decay. And depending on how much it's decayed, you decide if that's good or bad, and there'll be limits set.
Oh, okay.
And then you do the same thing on the oil chamber side. Similar thing, chambers are a lot bigger, so you would typically have an assist to pump air in quickly because you're trying to get it fast.
Yeah,
So you'd
yeah.
have like a 6 bar in very quickly. You'd close that valve and then apply the leak tester, and then you would do a similar decay test typically. And then what we do is you want to check that there's no leak between the water chamber and the oil chamber. So you
Ah,
then have the apply a pressure with the leak tester, for example, on the oil chamber, and make sure there's no change on the water leak tester. And
yeah,
that,
yeah.
as an example, so it can get tricky, and there's more complex and tricky ways to do depending on the product. But then
Yeah,
the
yeah.
quality guys are now getting a bunch of data out of that, but it's all quality related
Exactly,
and
yeah.
tagged to a
And
specific engine number, whereas that engine number's got nothing to do with maintenance. Yet,
correct,
if
correct,
the values are
exactly.
failing because of the machine, and that engine number is telling you that it's failing, but that leak tester or the engine number's got nothing to do with the leak tester asset. So connecting
Yeah,
the
yeah.
asset ID with the product ID is also critical.
Yes, yes, absolutely. And that's a fabulous example because it's really indicative of a challenge that all quality engineers or quality managers have, which is the data that you just described is fundamentally vector data. For each of these
Yep.
leak tests, whether you pump it up to 1 bar or 6 bars, and then test the pressure over time or record the pressure over time, it's basically a long time series of data in
Yep.
one individual data structure, which is vector data.
Yep.
So that data doesn't have a natural home inside of any of the operational systems. What I most commonly see is LabVIEW and Python. Basically, the almost all of the tests like that. They're actually, I'll add a third, which is the software, the application software from the test instrumentation vendor
Mm.
themselves.
Yep.
You occasionally see that. But any of those cases, whether it's in LabVIEW on a local machine, whether it's in some dedicated test suite software app, or whether it's in an ad hoc Python database. Python's a scripting language, not a
Yep.
database, but you understand.
Yep.
Um, whether it's in any of those three, it tends to be siloed right there. Whereas a lot of the quality folks and even the design engineers say to themselves, I bet if I carefully tracked each of those degradation curves, each of those leak curves over time, I could correlate those with particular failure modes. And in the cases where we're seeing more rapid degradation, I'm willing to bet I could correlate that upstream to the individual parts, to the settings on the machines that happened upstream of here. You can figure out what's causing it. Unfortunately, the most common thing today is pass fail, right? All of these tests. And in electrical equipment, it's identically the same. Sometimes it's a little bit more sophisticated and then they put like chirps or full spectrum inputs. But either way, it's a really rich data set, but then the output is just pass fail. If you pass, even though it was marginally passed and you've been degrading very steadily, you still pass and it's treated as though it was a perfect thing.
Yeah.
When an engineer, yourself, a quality manager, they know darn well that you can correlate multiple different varieties of passing behavior with an imminent problem.
Yeah.
And it's a perfect example that you raised. And so it's the quality dilemma that exactly mirrors the maintenance dilemma.
Yeah. The two interesting vector types that we spend a lot of time in is tightening data. So tightening a bolt, you can imagine how many bolts are in a car.
Oh, yeah, yeah. The
And
torque
we
data. Yeah.
and we typically on category A bolts, which are safety critical, like your wheel bolt, you have to log the torque and angle graph
Oh,
and
okay.
the nature in which that graph behaves, and the gradient of that graph is analyzed to determine
Love it.
the quality of the joint. That's live on a production line with hundreds and hundreds of bolting tools. So that's crazy. And then press
Yeah.
fit. So when you press in a bearing in many automotive components, you
Yeah.
monitor the force displacement curve. And two key things that are critical is you want to check when the force starts to increase so that you know that you've got the right alignment at the right depth. So
Yeah.
if the bearing is slightly skew, you might get the force too early. So we have to monitor the graph and put those limits in. And then at the end, you monitor the force and displacement so that, for example, and that there's actually been a gradual increase in that force as it gets to the final displacement. Because what often happens is you can imagine in a differential, if the machining hole was too big and you
Yeah.
press the bearing in, it would reach its final force because it's bottom out. But you turn the differential upside down and the bearing falls out.
It'll fall right out.
So
Or
you
or
have
over
to,
time with vibration, it'll migrate out of its
yeah,
position.
so you
Yeah.
have to measure the gradient of that curve. And we have to do that live on the production line as it's running. And the
Yeah.
prediction side, so you overlay a bunch of these, which is all theoretical. We've done some case studies of it, but nothing in production, where you overlay these force graphs, hundreds of them, and you start to create an anomaly detector that lets you
Yeah.
detect when you're starting to move in a certain direction. They're all passing, but you're moving in a direction, which is an early warning.
Exactly. Oh, that's an outstanding example. Yeah. Do you happen to know how are you collecting that data today? And do you use an analytics suite to overlay all those graphs?
We are we've developed our own solutions,
Oh, very nice. Very nice.
which as you're speaking, I'd love to share with you. And I think we come from a discrete manufacturing background, which is
Yeah.
somewhat different to the a process plant, and we've got a different, I guess, a different hat on. And so I'd love to share with you, to not bore the audience on the podcast, but we would definitely need to set up something, and I can show you the volumes of data we collect, vector data we collect, and how you analyze it post and analyze it live.
Very nice. Very nice. Yeah. Yeah,
Yeah,
I mean,
so leak
that's
testers,
brilliant. That's brilliant
leak
and hugely
testers.
valuable. And in this case, it sounds like regulatory requirement,
Yeah,
perhaps not on the bearing when you're doing an interference fit on a bearing. Perhaps that's not regulation required. That's just
no,
good quality practice.
yeah,
But on the torque curve, I didn't realize that it's not only you can't just use a torque wrench
yeah.
set to however many foot-pounds and then you get credit as long as you were torqued above that. You need to look at the entire rotation versus torque curve in order to properly pass.
In a car, they categorize the bolts based on safety critical.
Ah, really? Okay.
And we would call category A bolts the most critical ones, that if it comes loose, there's potential accident or death or whatever that is. And those
Yeah,
category A
yeah.
bolts have to be monitored. And then you get B and C. C is click the thing and it should be fine.
Yeah. Yep.
And then your B is kind of in between that, where you need to record a
Okay. So,
value, a static value, that it was 30 Newton meters, and it was a pass, and then you're good to go.
okay. Got it. Got it. Nice. Oh, that's great. A perfect example of quality data, Yanesh. And when you have time, I would love to dive
Yeah.
into that. That's super interesting and see how you're collecting that data, where it's going, et cetera.
Um, I thought, Glenn, let's kind of dive into your background, because you have, I mean, we've just touched the surface, literally, and I'm pretty sure if I asked you, let's go deep on Fourier analysis, that could be another 2 hours.
I
But
would enjoy that. But go ahead. Yeah.
but maybe talk me through your career. How did you end up where you are today?
Yeah, so the quick version is I'm an engineer with an MBA. So I have my bachelor's and master's degrees in mechanical engineering. And roughly 10 years into my career, I went back and got my MBA and then kind of switched to the dark side of doing mergers and acquisitions and business
Okay.
and finance. And I say that with love. I actually loved all of the business side.
Okay.
But yeah, so I spent the first decade of my career as a plant engineer. So on a day-to-day basis, I was out on the plant troubleshooting systems. It was mostly process plants in those early days, and occasionally some batch and pharma plants, less discrete in the early side of my career. So I would be at power plants, refineries, water treatment plants, et cetera. And I worked for a couple of different companies, including GE. But in all cases, my job was to troubleshoot the proper operation of the process from like a controls and process flow perspective, and to use predictive technologies to make sure that the machines are operating well. So we're not going to have a failure of a centrifugal pump, a motor, a compressor, a valve, et cetera. I loved all of that work, but at some point around a decade into my career, I realized if I wanted to just have a broader view, I was going to need to get some training formally in finance and marketing and everything that you get in an MBA. And so I went back to school, got an MBA, and then switched into product development, which was fabulous.
Wow.
So in the product development, I switched over to a discrete company named Fluke. You're probably
Yeah.
familiar with
Yeah. Yeah.
the classical yellow
Yep.
colored Fluke
Yep.
voltmeters. And yeah, for many years, I ran their process calibration business. And so in process calibration, we were focused on if you go into a plant and there's like 10,000 different pressure and temperature sensors, et cetera, as you just described before, you need to calibrate those and then leave that data somewhere so that you can prove either for quality or regulatory purposes that everything is going as it's supposed to.
Okay.
And so that was super fun because every day I'm swimming in real processes, manufacturing a high-end calibrator that can actually read these things, and lots of advanced physics and pressure and temperature and vibration and all the above. So for someone that sort of enjoys all of that, that was a fabulous portion of my career. Then I did mergers and acquisitions for about a year and a half, also at Fluke. And I think
That's
I
a big,
interrupted you.
yeah, that's a big jump from reliability and product dev to mergers and acquisitions.
It sure is. It sure is. And it was actually everyone says that it's stressful, and that's true. You're basically on call 24/7 because when a deal's happening, when you're in due deal, like you can't just push something off to next week because you have this Friday off because you have a barbecue. Like
Yeah.
you need to be on 24/7 through the weekends. And so I admit that I kind of burned out after a year and a half of mergers and acquisitions work, but wow, the learning was outstanding. And so for anyone that's earlier in their career, I would really encourage do a stint. Don't make a whole career out of M&A, but a stint in M&A, say 1 to 2 years, is just amazing learning. Because what happens is on the backside, you look through an entirely different lens. I can't point to any one specific, like, oh, here's a technical point that I learned in that time that was transformative. It was really more a mindset. And what you'll find is if you're doing M&A at a really large corporation, they're worried as much about downside risk as they are about upside growth and return. And that wasn't intuitive to me. So I spent to artificially quantify it, 70% of my time was inventing all of the plausible downside scenarios that could happen with a particular company or product or market, and then convincing myself that those were not going to play out, or if they did, we had some kind of a mitigating factor that could help it. And then maybe 30% saying, okay, assuming no disasters happened and we have perfect continuity of manufacturing and personnel and all of that, now, can we grow this thing? Can we have synergies, as they call it, inside? If we absorb this company, are there synergies in the cost side, meaning we can kind of like absorb different factories together to be more efficient, maybe use our supply chain heft in order to get lower prices from their suppliers, et cetera? Or is there revenue synergies, which are always the more fun one, where if we were to rebrand this already really great product and then push it through the commercial channel of a much larger company, could that do a lot of revenue growth?
Yeah.
So while I wouldn't point to any one individual thing that I learned around there, the mindset that the CEO of the large company has to adopt when doing mergers and acquisitions really changed the entire way that I look at a company as a whole. And that's why I would really recommend it to anyone, especially younger in your career.
Okay. And so you were at Fluke with M&A and then?
Exactly. Yeah. Then I went on to a company called Novanta, and I was the president of a high-end laser manufacturing business called Sinrad. So Sinrad is the laser manufacturing business, and Novanta is its parent company that is a publicly traded entity. That was a whole lot of fun, and it was photonics is a different world. Have you ever had any experience in photonics, Yanesh?
With laser, I, not myself directly, but there's some of my colleagues in battery manufacturing in the car. You have to laser weld the bus bars onto the cells.
Oh, fabulous! You probably use a fiber laser for that, then. Yeah.
Yeah, Trumpf obviously being one of
Trumpf.
the.
Yeah. Wonderful. Yeah. Yeah.
With what was interesting for me was the autofocus required because of the varying heights of the cells,
Yeah.
and because the bus bar is so thin, the precision required to get the right depth of the weld is so critical. With this varying product in height of the cell, they're not consistent. Was really interesting, and they created this autofocus within the laser head itself that allowed and you have to weld like kind of 6,000 tabs an hour. So it's super fast.
Yeah. Yeah. Yeah, you nailed it. And I had no appreciation of that until I entered the photonics business. But I pictured lasers as being relatively easy to manufacture, these perfectly straight beams. I don't know where I got that image from, but they're just perfectly straight. Like by definition, it's a laser. Its whole thing is it just spits out a perfectly round, perfect beam that doesn't diverge. And that couldn't be further from the case. It's extraordinarily difficult to get the beam collimated properly, and it diverges or converges, like it goes all over the place. Like photons do not like being in a nice little tight perfectly circular thing. They want to diverge, and you have to go through all ends to get the energy focused directly where you want it to in an application like that. And so it was amazing. What I liked the most about it, beyond it was, a privilege to get to run that company, um, the amount of technical difficulty in making a quality photonics product is 10x what I expected it to be. And so if you think you're a good quality engineer, go work in photonics. And that will be a rude awakening for you. A nicer way to say that is if you know someone who works as a quality engineer in the photonics world, go give them a hug. Their job is one of the hardest in the universe, and support that person with everything you've got. Make them dinner, bring a lasagna to their house, but believe me, they have a hard life.
And is it all centered around the lenses, or what part of that product is difficult to get right? Or
Yeah, so
everything?
it's all of the above. So if you think about the chain, there's really sort of three things that happen. First, you have the laser source. We sometimes call the laser source.
Yeah.
Then it has to go into some type of a steering mechanism. So rather than just spitting a laser beam out, there are several different steering mechanisms to put the beam on a very precise place on the workpiece. You were describing a focus head, or we sometimes call that a cut head. In this case, it's a welding head, but its job is to take a raw beam and point it at a very particular depth and breadth and focus plane on the actual workplace. A big way to do that is using mirrors or galvanometers. And so, roughly speaking, 80% of the time you'll use what's called a scan head with mirrors and galvanometers that are literally these little high frequency mirrors that change where
Yeah.
you're pointing the beam. The other 20% is exactly what you described, something like a cut head or a welding head.
Okay.
And then you have the application workpiece itself, which gets into precision motion as much as it does photonics, because once you've figured out exactly where the laser is going to converge and what the spot size is and how much energy will be directly in that very small spot, then you have to make sure that the thing that you're welding is exactly in that spot,
Yeah.
which inevitably requires tremendous motion control, very precise motion control. And so every step of the way in making the laser, since they don't just spit out straight beams, they have all kinds of power fluctuations. The beam wants to converge and diverge. It converges and diverges at different rates in the different axes, so it's never a perfect circle. And even in the case of gas lasers like mine, even the tiniest little particulate matter or anything foreign inside of the gas laser will react with this very careful mix of oxygen and xenon and helium and neon, and it messes up the entire performance. And so
Oh,
every
wow.
step of the way, there's like this laundry list of extraordinarily difficult problems that you have to solve. In the case of the mirrors, it's a process industry, actually, the mirrors. You have to do, it's typically anywhere between 10 and 25 different, very fine precision coated surfaces. And that's not easy. That's a batch process where you coat layer after layer after layer to get just the right characteristics such that you don't absorb all of the laser heat, which would then fry a hole directly
Yeah.
in your mirror, but rather you reflect 99.9% of it so that you don't burn up. And that's extraordinarily difficult. And then you have the motion control problem. I'll stop because I'm going to depress all of the listeners. But my goodness, the entire industry was so hard. I kind of wish somebody had told me that before I
Yeah.
before I jumped into it.
I'm glad you told me because I had no idea it was that complex. It was just a box that I could buy from somebody and it worked. I had
Yeah,
no idea.
exactly.
I'll go and give
Yeah,
him a
my
hug next time I see him.
there you go. Yeah, my prior experience was with many, handheld diode lasers that you click a button,
Yeah,
it's straight, it looks great. I was like, oh,
yeah.
how hard can that be? And it's really hard.
Interesting. So what is the name of that company again?
That company is Synrad. So the
Finrad. Okay.
company that I was the president of is
Yeah.
Synrad.
Okay. And
And
then,
it's right here in the greater Seattle area. And
okay,
so it's great. I live close by, so I still get to see all of my old coworkers quite frequently, which is great.
that's cool. And then from there?
From there, I went to Weights, a predictive maintenance company. So Weights is the
Yeah.
sensor that I was holding here. I was the chief product officer at Weights, building all of the systems that we just talked about, figuring out how to get vibration data from a sensor to the cloud, analyzed properly, and how to get the CEO of Weights has a tagline, a sensor for every situation. Rob Ratterman is the CEO there. And I love his vision. His goal is to have a sensor for every situation. So from a predictive maintenance standpoint, whatever machinery flaw that you might incur on your floor, Rob is, I don't know if I can curse on your
Yeah.
podcast. Rob is hell bent. Rob is heck bent on getting a sensor for every situation so that we can get that data into a platform like Weights and then perform all of the advanced AI algorithms and predict failures. And so that was a fabulous company. And I'm thrilled to say when I stepped out on my own and started Abelara, it was with Rob's blessing, Rob, the CEO there.
Okay.
And he's been super supportive, and we're still very tightly partnered with Weights. So we're a representative of Weights, and we do lots of trade shows together. So great relationship with the Weights team. And I admit that I'm biased in the predictive maintenance world. They are my favorite.
Okay.
Your listeners should know there are multiple options out there, but I am openly biased in the direction of Weights.
Nothing wrong with being biased. It's good to take a position.
There you go.
Whether that position is scientifically right or not is irrelevant. It's about taking.
We could debate that ad infinitum. Yeah.
Yeah. So tell me about your current adventure.
Nice. So the current adventure is I co-founded with a gentleman named Dylan Dufresne, and our company name is Abelara. What we do is digital transformation. So our mission is to make digital transformation work for manufacturers everywhere. What we found is the biggest difficulty in properly implementing either an AI or a UNS or even an MQTT broker or any kind of digital transformation initiative is what we call the missing friction in the middle. If you were to take a top-down view of all of the applications that are used, from an IT perspective, you could think about a manufacturing org as having like a supply chain software, an ERP, a PLM, an engineering suite. Those are traditionally called IT. However, when it comes time to manufacture, you have to go down the OT stack, such as MES, SCADA, PLCs, instrumentation, IoT, et cetera. And somewhere in there, you have to also integrate the maintenance data that we discussed. What we found is that there was always a big disconnect between what we would call the executive or the leadership team and the ground reality. And it's that messy middle where we intentionally surface the friction, surface what's going wrong, and then find a way to solve it through clever integration of all of these different data types. So in a nutshell, what we do, it's typically through a workshop method, but we'll go through each of these 10 applications. We will articulate the strategy that they're using because some plants, the vast majority of the people don't realize, oh, so we're an MRP house. They do it and they're doing it properly, but they weren't previously aware that that's a choice on a spectrum between MRP and lean. Yeah. Each of the 10 boxes, we have a methodology that we go through to articulate the strategy that you're using, the architectural trade-offs that you have made inherently in doing so, whether you're conscious of them or not. This is the trade-off that you've made in making this choice. And if your goal is to optimize revenue, throughput, cost reduction, quality, whatever the case might be, here is a way that you can integrate all of the different data types from scalar all the way to tensor in a way that unites the realities on the plant floor with what the executive suite is seeing. Lots of details in addition to that, but in a nutshell, that's what we do. And this is, I have to admit, it feels like sort of the crowning achievement of my whole career. I'm deploying everything I've learned at all of those other jobs on every single project that we deploy right now. So I'm thrilled to have a brilliant co-founder in Dylan Dufresne. He's our chief architect, and he was a system integrator that's been in the trenches for over a decade, integrating every plausible maintenance and or operational system at a manufacturing plant with every other plausible kind of database. So he's kind of a wizard. He can make anything talk to anything else. And between the two of us, we've got a pretty effective methodology going.
Yeah, and I think it comes down to defining the methodology. The tools are available, but defining a principle and a methodology, like you say, is I think the missing link. And that's not, I mean, you have to have a strong technology understanding, but it's not a technology problem.
It's really not. Yeah, exactly. It's much more organizational workflow problem, if you will. It's that was very well stated, Yanesh. That was the thing we saw everywhere. Like you can find people with deep expertise in SCADA. You can find deep MES experts. What's really hard is to find a company that can stitch together all of these in a coherent way using some type of repeatable methodology. And that's what we believe we've built. And of course, we're refining with every subsequent project. But so far, so good. We've been having a lot of fun.
That's great. If you had the opportunity to have a greenfields factory,
yeah.
Have you given any thought to that data structure? Yeah, I mean, we live in a world where it's not ideal, right? You have existing stuff, and you have to always try to connect what's there with what's not there. You're making compromises along the way. Have you thought about the uncompromised, perfect data structure for I don't know, a biscuit manufacturing, a cookie
Most
manufacturing plant.
Yeah, most definitely. I admit I haven't done it specifically for biscuit manufacturing, but but for manufacturing as a
Yeah.
whole, most definitely. And yet, the basic idea is you need to take only the relevant piece from each of those big 10 applications and put them into a single one. So right now, there's a distinction between the supply chain suite and the MES and the PLM. It's sometimes called the golden triangle, in that you have really critical information about the design, the bill of materials, and how that bill of materials eventually turns into a manufactured product on the plant floor. These reside in completely different systems, and it takes great pains today to integrate them. But the feedback cycle is so crucial that they should really be in the same system. And so if I had my way, something resembling an MES would hold all of the core data from all of those, and would be composable. So by composable, I simply mean that a factory can easily create data structures on the fly, like in your situation where you need torque curves for the Class A bolts, and or you need leak test curves to be stored in some coherent data structure. If you use a system like an MES with the ability to handle non-scalar data and integrate to an ERP, you can do 95% plus of everything you would do in all of these separate situations, except customized to your own plant. And you now don't have to take on the giant system that is today a PLM or an SCP system. Because the dilemma is all of those, by definition, those vendors did a great job. Like, they're serving the entirety of the manufacturing world. They have to build in all of the functionality that the entirety of the manufacturing world needs. Any given customer is only going to use a small fraction of that, and the rest is effectively waste that has to be maintained. Instead, if you could do just some really targeted feedback loops in the functionality of a PLM and an MES and an SCP and put that in one suite, that's huge. You can then integrate to a bare bones ERP that's focused exclusively on financials, and then all service and operational details can reside directly in this magical SCP, MES, PLM suite that's in the middle. And then at the controls layer, it's amazing how effective simple PID controls on a PLC are today. I can't believe I'm saying this, but that's actually not the biggest area for improvement. It's the most fun mathematically to dig into, is to try to think of the entire world runs on single input, single output PID loops. Surely there's some multivariate control methodologies using AI that would be better. And there definitely are. However, that is not the best vector for improvement. It's really that middle ground in the MES layer.
I agree. I think PLCs work really well, and I don't think that's where the step change is going to come from.
Yeah, yeah. Improvement can be made there for sure, but it's not the first thing to tackle.
No. And I also think that safety plays a big role, and PLCs have got the safety element of a machine waxed. Yeah, I wouldn't go and re-engineer that purely. It works.
Exactly.
And I don't think there's a step change to the way it helps. It wouldn't help the business in a big way to optimize that. There's opportunity for sure, but I agree with you. It's that middle layer that is a little bit fuzzy. One thing and we'll set up another discussion for sure, is that I think that where I feel we've potentially been led awry is we have different manufacturing types. Like I speak a lot about discrete manufacturing, and I obviously follow Walker, and he's pretty popular. And I've tried to understand UNS, and it makes a lot of sense for specific kinds of manufacturing. But in complex discrete manufacturing, where you're making these unique products through the process, it requires a different architecture. Like the ISA 95 does not work in a car factory. Because of we're building to a bomb. So you pass the bomb down, and the bomb actually tells the PLC what to do, because the bomb requires certain combinations of parts to be fitted together. So it's a bomb-driven production line. It's not a batch-driven or a recipe-driven. And so I think that what happens is we try to shoehorn everything into ISA 95, and then we compromise. I think we shouldn't be shoehorning anything into everything. Everything into one
into any one standard. Yeah.
And I think we should be dividing manufacturing up into the manufacturing type, because I think oil and gas is very different to cookie manufacturing, very different to car manufacturing. Yet we all try to use ISA 95, and that doesn't make sense.
Well, Yeah, well stated, well stated. And while I'm sure we all admire ISA 95, you can do a heck of a lot with it. But there is no, I like how you said that. There is no one standard that I would say this is the golden ring. Like use only this standard for nomenclatures because the manufacturing world is diverse and has almost an infinite variety of different data types, and no one standard by definition could ever capture all of that.
Yeah. And I think if we started to build out standards for the different manufacturing types, I think we'd be more successful in standardizing. Because I'm a big believer in standardization because that
Yeah.
helps with skills, helps with communication protocols, and there's a huge advantage of standardization. But trying to bulk everything into one and then trying to standardize, it hasn't worked. Like it just hasn't worked.
Exactly, yeah. And so there are great standards out there, ISA 95 being one of them. You should consciously deviate from any given standard when you look at it and it just doesn't pass your sanity check. You're like,
Yeah.
I'm forcing a standard onto a process that doesn't look like that. That's the moment that you should make a conscious decision to deviate from the standard.
Yeah.
But you'd be crazy not to at least consult the standard first
No,
when
no,
you're setting something
of
up.
course.
And yeah,
Yeah, of course, because then like I think the standardization helps with one of our biggest challenges, which I'm sure you face, is skills. So
yes,
if you
yes,
could follow a standard, you could get people trained on the standard.
exactly.
And it's a lot easier to scale a business or a product or whatever that is. But
You
yeah,
got it. And then when they switch lines or factories or even industries, if those industries are nominally using a same standard base, it's a piece of cake.
yeah,
Or let me say, at least it's much easier
yeah,
to switch over. The learning curve is greatly reduced, and that is really useful
yeah,
because I think in every nation we're facing great difficulty finding qualified manufacturing engineers, manufacturing technicians, basically anything to do with
yeah.
manufacturing.
It's
So.
not sexy anymore, unfortunately.
No, unfortunately not.
Yeah.
And so we are starving for qualified personnel.
Awesome. I don't know if you have any other comments.
No, I think this was really good. The a couple of themes that we didn't get into that maybe we could on a future
Yeah.
podcast. The whole idea of ERPs. Let's not do it right now, but you know the old adage that no ERP has ever been implemented on time or on budget or properly. Like there simply does not exist a
There,
positive ERP case
there
study.
are more CEOs that have been fired because of an ERP implementation than hired.
Isn't it amazing?
Yeah.
And yet it is like a multi-billion dollar, multi-hundred billion dollar industry. Everybody has to have one. And it's a really strange state of affairs. That's one of the biggest things that we're seeing changing is the old idea of a monolithic ERP that tries to do everything. It's actually the same exact spirit as the standard discussion that we had. You might think about the last couple of decades as the ERP taking over the world and trying to be everything to everybody and doing it poorly. The future, we believe, will be much less than that. We're seeing a very palpable pendulum swing of getting functionality out of the ERP where it's clearly not naturally suited. Like talk to any service department everywhere, they'll hate their interface with their ERP. I almost accidentally said an actual name of one, but nobody likes it. And so increasingly, what we're seeing is a UNS style approach where you have harmonized but integrated individual applications for all of the things that you're doing, and a more bare bones ERP. It still has to be there for the financial backbone. You can't operate a company without it. But people are increasingly offloading functionality out of the ERP in order to de-risk ERP migrations, and frankly, to get better service out of what's now capable on the plant floor. There's a lot of technology that the ERP simply doesn't incorporate that you've got to get the functions out of the ERP to use them.
Yep. I think it's I'm always I have a philosophy of the previous way has always been a top down. So you had the
Yep.
finance department that pushed systems down into HR, into training, into the MES, into the shop floor, into warehouse management, and it went all the way down. And then it didn't, like you say, there's data structures and thinking, and that's different.
Exactly.
And it just stopped, and it just couldn't go any
Yep.
further. And then there was this. It ended up being a mess. I think
Yeah.
that if we just take a step back and realize that factories make things and start developing the systems from the bottom up. I mean, we have the
Yes.
vision for the big picture, right? That's clear. Need to be efficient, make money, all that kind of stuff. That's kind of obvious. But I think from a systems level perspective, we need to put the product, the operator, the technician first and develop systems from the bottom up because we're all there to serve that. The objective of the
Exactly.
factory is to serve the product, the operator, the technician, and that's it. And everything should be developed from that point up, not the other way around.
That's amazing. Couldn't say it better, Yanesh.
Yeah.
The factory doesn't exist to create an income statement, a balance sheet, and a cash flow statement. The factory exists to create the physical product that you're making.
Or the IT
And
department, which is the big, in my opinion, the tail wagging the dog.
for sure, no question, no
The
question.
IT guys don't like me, but that's what I believe.
And we are fully aligned there. And the great news is we're seeing that, right?
Yeah,
Like
it's
there's
changing.
been enough. It's not even a secret. Like everybody knows that ERP implementations suck. They cost an obscene amount to implement. And so now we're getting into this red versus blue data. That again, we'll kick this to another call. But there, if it's a new term, so you might not have heard it yet.
Yeah.
But there's this idea of red versus blue data. Red referring to data structures that the finance world needs, or let me say the executive world needs. They want to standardize across multiple plants. And so if you picture like they can mandate down to a certain level and say, this is what I need. I need to be able to compare the working capital at multiple different plants, as well as the overall efficiency or the return on invested capital, whatever it is that they want. We call that red data. You do have to standardize to a certain extent on that red data in order to deliver those apples to apples comparisons to the executive team. The important point is that doesn't have to happen in the ERP. And that's what's different now. It used to be implicitly assumed that any of the standardized data meant it must be literally the ERP that pushes top down all the way as far as it possibly can. And now that is a little bit insane. And so clearly the bottom is pushing back up, or the front line, if you will, is pushing back. And we've used this terminology, the red versus blue data, where you can now say to finance, to the executive team, we completely respect your need for that apples to comparison of those metrics across all of those plants. That's the red data. Here is the API. If we promise to give you that, we hereby take control of everything that leads up to those numbers. And then that is the blue data. So we'll standardize on the red data on the factory floor. However, we, the factory floor workers and engineers and quality managers, we hereby own all of the blue data, which is literally everything else that happens. And then we will plug into your red data requirements, but we hereby take control of the entirety of the blue. And that's what's playing out, which is super fun. It's a much better division of labor.
So I am due to be in Seattle in March sometime, and maybe we could do it face to face.
Oh, I would love that. I would love that. Absolutely.
Yeah.
Yeah, we have a small, admittedly small office, but we can set up microphones, and
Yeah,
that would be wonderful.
or even if we just have a catch up for coffee.
Yeah, yeah. Even if we just have a coffee somewhere, like you said, that would be great. But yes, please let me know of your travel plans, and we'll get together in March for sure.
Cool, and I'll definitely set up some time with you maybe before that, and I'll run you through a little bit more about our business. I think you'd find it very interesting based on the data and vector data and all that kind of stuff.
Yeah, I would love that. And we can either just do it personally one-on-one. Feel free to record it and like
Yep.
issue it as a podcast. You just tutoring me on how it all works. But I would love to. Either way, please count me in.
Cool. Glenn, thanks a lot. I really, really appreciate you taking time out of your early day to chat with us. I learned a huge amount. Thank you very much. And
I'm humbled if you did.
yeah, absolutely. Yeah, it's not often that I get to speak to a person that has developed a vibration product or been part of the team that has been the president of a company that knows how lasers work and is now entrepreneurial, starting their own business and really, in my opinion, understanding the real problem in digital transformation and helping customers solve it. So that's really amazing for me.
Oh, wow. Well, that was super humbling, Yanesh. Thank you. That was very kind of you to say. That was very kind of you. And likewise, of course, you were sitting there. It's blurred, but you literally have a factory right in your background there that you're running. So
Yep.
it makes the conversation so much more palpable because you know exactly what you're talking about. You're literally running a factory, and so I loved it. Let's do this again. Let's do this every couple of months or something.
Yeah, we should. Thank you very much, Glenn.
Okay.
Have a good day further.
Talk
Bye.
soon, sir. Bye now.